Our work addresses controlled flight into terrain, CFIT, a significant cause of aviation accidents. We propose a parallel autonomy system that takes control when collision is imminent, operating continuously in the background with a forward-looking motion plan ready for immediate execution. Generally, existing terrain avoidance systems rely on predicting trajectories for predefined maneuvers. The baseline approach utilizes a single predefined maneuver, typically a wings-level 5G pull-up, predicting its trajectory with an ODE solver. More advanced systems employ hierarchical planning with multiple predefined maneuvers, such as varied turns and G-pulls. However, these approaches limit themselves to a predefined subset, representing only a fraction of the complete solution space, resulting in a conservative approach with potential false alarms. To address this, our methodology generates terrain avoidance motion plans in real time based on the aircraft's current state vector and a digital elevation model of the terrain. The planning process involves two steps. First, sampling-based planning uses generative adversarial learning to bias search toward collision-free reachable regions. Second, we utilize differential flatness to ensure dynamic feasibility and map the escape trajectory to state control trajectories. Training our generative model requires a dataset of collision-free reachable regions. We generated this dataset by executing a wide range of predefined maneuvers, filtering out maneuvers that lead to collisions. These predefined maneuver trajectories are processed and dilated against a 3D voxel map conditioned by the aircraft states to produce a reachable set represented by a 3D voxel. We employ conditional generative adversarial networks to learn the distribution of high-quality sampling regions. The generator network is conditioned on the digital elevation map and the aircraft state vector to produce a generated heuristic region. The discriminator evaluates authenticity against ground truth, driving the generator to produce increasingly realistic outputs. Here you can see learned high-quality sampling regions for different initial conditions. Rapid trajectory planning is performed in two steps. First, we employ RRT, rapidly exploring random tree, for waypoint generation, sampling waypoints from the generated reachable set of the 3D voxel. Second, we generate the final recovery trajectory by optimizing a minimum jerk trajectory through these waypoints, utilizing differential flatness to ensure dynamic feasibility. This simulation shows our complete system successfully avoiding terrain collision with smooth, dynamically feasible maneuvers, demonstrating end-to-end pipeline in action.